Okay, thank you very much for introduction. And let me say, first of all, thank you very much for the invitation of this very interesting workshop. As the chairman introduced, I talk about this title and contents listed in here. For this gray part, slightly subtle changes, but if I have time, I try to quickly explain about this issue as well. Let me start by showing my favorite slide, which is originally made by Marek. He nicely organized the questions that hadron physics has to answer. But here, but he also made a nice comparison of those items with the items in the social life. That is the reason I memorized, and I also like this much. Actually, I'm a Japanese, and I didn't know the last phrase of this piece. Maybe you know. But because nevertheless, he kindly explained the meaning of this, so this came to my dictionary as an important phrase in my life. Okay, I think as we can share this fact, a difficulty in QCD is actually variable dynamics, or more explicitly, effective degrees of freedom depend on the energy scale of phenomena. On the other hand, the data is plenty that brought much information for building good effective models. And one of them is the Quark model. If the model is more than a working hypothesis, we must be able to find a link from QCD. And here is one scenario that is the use of instanton vacuum, which is symbolically expressed by this picture made by Derek Lineweber. Theoretically, this picture is supported by, for example, the Banks-Casher theorem, which is also verified in lattice QCD. Based on this, chiral symmetry is spontaneously broken, and we can introduce an effective quark interaction that leads to several convenient forms of effective quark Lagrangians. For example, the non-Abelian racino is one of them. So one of those models is the so-called chiral quark model that was formulated nicely by Manohar and Georgii. Based on that, we can postulate an effective theory of massive constituent quarks interacting relatively weakly with gluons and also with the Nambu-Goldstone bosons due to spontaneous symmetry breaking of chiral symmetry. And I think this can be the basis of the non-relativistic quark model. So in the following several slides, I just quickly show some evidences that support those constituent quark model. The first one is the magnetic moments of octet variance. And as this table shows, by including the possible relativistic corrections, the model works pretty well in comparison with the experiment data. The second example is the masses of octet baryons, the formula of which can be summarized by this simple equation of 3 parameters. And by giving suitably these parameters, this simple Hamiltonian can reproduce nicely the masses of those octet variants. Actually, in fact, the success of magnetic moments and masses considered to be a realization of SU3 flavor symmetry with small breaking. In fact, I think there is yet what we may call dynamic evidence of constituent quarks. That is the axial coupling. It is well known that non-relativistic quark model predictions of the nucleon GA is just 5/3. That is the spin isospin matrix element in the quark model. But this value is overestimated as compared to the experimental value, which is 1.2. However, by taking account the relativistic corrections reflecting the motion of quarks inside baryon, it is shown that the agreement is slightly, well, significantly improved. This applies not only to the nucleon, but also for some of the heavy baryons like lambda C, sigma C, and also the decay of the D-star mesons. Yet an interesting example is in the decay of the Roper resonance of the nucleon. It is considered to be a radial excitation of the nucleon, and hence in a quark model, it has the same spin structure as the ground state nucleon. Only the radial wave function is different. The decay is then computed by the axial current, which is nothing in this case, but the spin isospin matrix element. But radial part is simply 1, nothing. And so therefore, the transition matrix element vanishes because of the orthogonality of the radial wave functions. But actually, in reality, because of finite momentum transfer of this decaying particle, Mach ion, the matrix element remains finite, but is very much suppressed. As this comparison shows, namely, the non-relativistic piece is just 12 MeV, while the data is more than 100 MeV, just about 10%. However, again, by taking the relativistic effect, taking into account the quark motion in a nucleon, the number can be reduced this much. So I think that this is one of the evidences to show the reality of the current quarks. Okay, having said this much to support the quark model, let me go on to its application to TQQ. For this, I should mention that the Marx and his collaborator John Rosner's contribution is very important. In fact, they have predicted the state in here drawn by green line, which is surprisingly well agree with the recently observed data. Therefore, what I will present today is a kind of confirmation of their conjecture prediction by, in some sense, a brute force method of the quark model. Perhaps I do not have to say very much about recent data from LHCb, only by mentioning that they found a very sharp peak just below the DD star meson threshold. So why TCC is interesting? First, it gives partly an answer to Marek's question, for example, who with whom. Second, the system contains two energy scales, and the resultant physics is a delicate interplay of two dynamics. Okay, one is the light, the other one is the heavy dynamics as compared to the energy scale lambda QCD. Partly because of these reasons, there are by now 51 theory papers appeared in Inspire. I've checked this number today. But still, we have to be able to explain with less assumptions its existence and structure. This is the reason that we started our work in a more standard model, that is the Quark model. So let me try to explain the two energy scales. One is the strong interaction scale dominated by the dynamics of light quarks, and the other one is for heavy quarks. And in fact, what Mark emphasized in their previous studies, is the importance of the heavy quark dynamics, where the dominant interaction is due to color-Coulomb interaction of 1/r type. Because of their heavy mass, the Coulomb binding becomes larger for heavier quark masses, giving more chance to generate stable states. Another important point is the color factor that provides a very large attraction for QQ system. And also for QQ, there is a strong attraction, but with half strength of this QQ bar. So now the stability of the Tetraquarks system is checked by comparing the threshold masses to which those tetraquarks may decay. One is a DD star, or the other one is the, for example, J psi pi, like say, namely the open heavy mesons here, or hidden heavy mesons like here. The different heavy quark combinations like heavy, like here, or heavy anti-heavy, together with the energy scale of lambda QCD that governs the mesons, DD star, it is not actually difficult to observe that in a heavy quark limit, this TQQ tetraquark remains stable without decaying into lower two mesons. On the other hand, this here, TQQ bar, eventually decays into those two mesons, one of which is the heavy quark and anti-heavy quark pair, having a very strong binding energies. So the stable heavy quark is expected almost exclusively for this kind of combinations. A bit further about the quantum numbers. For the likely heavy quarks, for the like heavy quarks, similar heavy quarks, such as CC or BB, due to the Pauli principle, it is expected that the most favorable spin parity is 1+, and also we can consider the isospin by the light to Q bar quarks, which is 0. So let me try to go on our brute force method for the study of TQQ prime in general. For this, we employ a method of solving a few-body system, that is the Gaussian expansion method developed by a few-body physicist, typically Emiko Hiyama and collaborators. For details, I have to refer to references, but the essence is that we have to introduce several sets of Jacobi coordinates. Then we prepare variational states in a Gaussian basis for each those Jacobi systems, and then diagonalize the Hamiltonian by using a supercomputer. All right, now for the Hamiltonian, we take a very standard form containing the non-relativistic kinetic term Coulomb plus linear potential and spin-dependent force like this. So there are several parameters in the model, but it is very important the model should be able to reproduce a simpler states like mesons, these mesons. This is very important because to check the stability of the tetraquarks, because we need to compare these two sectors. So we did it, and we observed that our quark model seems to be working all right. But still there is some uncertainties, ambiguities, for which we expect the order of 10 MeV or so this is the preparation. I quickly show the result. This is it. We have actually computed this TQQ prime state with various combinations of quarks. In a quark model, therefore, we have found altogether 6 states against strong decays. As predicted previously, the mostly deeply bound state is realized with binding energy as large as almost 200 MeV, which is sitting here. On the other hand, the TCC, which I've shown today, is sitting here with a binding energy minus 20 MeV something. So in comparison with the data, this seems a bit overbound. But I hope that they think this could be within the model uncertainty. And I think this corresponds to the observed state. So, for example, if we weaken the strength of attraction for this state common to all the other states, we have seen several shallow bound states. They might disappear. But for other deeply bound states, like here, maybe here as well, these as well, are expected to be stable and stay as a bound state. By the way, here I show a kind of systematic plot depending on the reduced heavy quark masses. Once again, this is the original picture is from the Marek, from this paper. And I put our result by these blue dots. There is some differences between ours and their plots, but general tendency is the same. So therefore, their predictions and our tendency, our brute force calculations similar, and those features are most likely the correct features of the heavy tetraquarks. Okay, to actually further verify the quark model predictions, I made a comparison with the lattice calculations. Those values with the references, the result by lattice by 1, 2, 3, 4, 5 previous works. Actually, the lattice results scattered, but at least for the most deeply bound state, the tendencies are similar. So therefore, very crudely speaking, the quark model and lattice result are quite similar. Now let me go into a bit the structure of those states. So because we have several stable states, but to see the structure inside, we'd like to focus on the two states. These are the two states which we have seen in here. Okay, so just pick up these states. One is the deeply, the other one is the shallow bound state. To do that, we have computed the so-called density distributions of 2 quarks in 4 quarks. So actually, the precise definitions is like this, but this is not very important. Very intuitively, we can say that the average interquark distance of the 2 quarks, we pick up 2 quarks among the 4 quarks and measure the distance. So for deeply bound state, heavy 2 quarks, BB, is very much close, yeah, but QQ bar or Q bar heavy quark is more extended. So we can draw this sort of picture. Looks like singly heavy quark baryon. This is the structure for the most deeply state. The other one is shallow one. Now, from this picture, it looks a bit complicated, but after some thought, we expect that this has a molecular-like structures like this. So again, this kind of situation is, to some extent, we could have expected prior to those brute force calculations, but it's a kind of fun to explicitly observe the difference in these structures in a deeply heavy and weakly heavy resonance bound states. By the way, how much time I can speak? Maybe 5 minutes or 10 minutes?
Yeah, I think nominally the time is gone, but do you think
done already?
Yeah, it's 25 minutes already. Do you think it finish in 3-4 minutes?
All right. Then this is the story for the Tetraquarks. Because I saw the audience more formalist since yesterday, the other day. So I put one subject of the, again, phenomenology of variance, but based on holographic QCD. So I think I'd like to discuss this issue with you. So although I prepared the resonance states for TQQ, I can quickly skip this. And let me try to show spinning. Please allow me 5 minutes, no more than 5 minutes for this holographic model. The reason I want to discuss from the phenomenologist point of view, originally our starting point, chiral quark model contains the pions. So where is the influence of the pion or meson dynamics? And in an extreme sense, when quark degrees of freedom is integrated out, the theory will become the one of the only with pions or mesons. That is, in some sense, the holographic model, and for which I depend on the so-called Sakai and Sugimoto model, which actually shares for baryon physics with the old wisdom of the square model. So this is a very kind of quick cartoon of the idea of the Sakai-Sugimoto model. The effective theory of them is actually made by the 5-dimensional space with the flavor gauge theory. So the baryon, which is described by instantons in a 5-dimensional space, which is holographically projected onto the 4-dimensional space-time corresponding to physical variance. The important point is that in instantons, there are several integral variables in solving the equation of state. They are physically corresponds to the location of instantons, size of the instantons, or the rotational angle of isospin orientations of isospin. They are regarded as dynamical collective variables of the instantons, which are quantized to generate the physical state. That is the basic idea, similar, essentially the same as the square model. So I just show the quickly the action, which is written by the flavor gauge field in a 5-dimensional space, together with the characteristic metric H, which is a function of Z variable, extra dimension, 5th dimension, with those parameters. And the remark is that, again, all right, this is probably well known, the BPS type instant solutions available under some approximations for this Sakai-Sugimoto model. But an interesting observation, after all, together with those metric H and the structure of the flavor gauge field, the instanton solution can find a stable size in a configuration space. And eventually we can write down, starting from this action, effective Hamiltonian for the collective coordinates with this simple potential. As a result, the wave functions in terms of these collective coordinates really looks like a harmonic oscillator type wave functions, which are very simple for the oscillation of the radial directions, and also to the oscillation to the Z direction motion. Actually, these two motions correspond to the radial excitations of the nucleons corresponding to the Roper-like excited states, and this corresponds to the negative parity resonances. So in that way, we can construct the nucleons and resonances as well in those models. And here is a quick comparison of the models with experimental data. They are really details, but generally speaking, I would say this model can compare with the data pretty well. And in particular, from the phenomenological point of view, interesting thing is that in this model, the Roper state of the nucleon resonance, 1/2 plus spin parity, degenerate with the negative parity states, 1/2 minus. This actually feature is very difficult to reproduce in a simple quark model, but this model can explain very nicely. So after observing this fact, we have decided not only those static properties, but also the decays of their resonances recently. And one of them is the decay of the Roper resonance, which was actually very suppressed in the quark model. And we were interested in what would happen by using this holographic model. And the method is just compute the axial matrix element, because the 1 pion decay is related to the those axial coupling through the Goldberger-Treyman relations. So therefore, first define the occurrence in the 5-dimensional model, which is like this. And the strategy, the method is more or less known. And but I want to say, in deriving the matrix, this operator, actually current in the holographic model, contains the rho square. So our task is to take expectation value of this rho square operator by the rho bar wave function in terms of rho variable and the nucleon variable. They look like a harmonic oscillator. Ground state in the nucleon looks like this. The rho bar state looks like this, oscillating or nodal. But because of the presence of those rho square, this matrix element becomes finite. This is very much different from the features in the non-relativistic quark model, which gives the 0 in here, because nothing appears like rho square in there. The reason of this is that this state in a holographic model appears as a collective state for this rho bar. So the comparison of the experimental data looks much improved. And also it happened that we found a model independent relation between the actual couplings for the nucleon and the actual transition coupling of the NN star and the rho bar-like state in an analytic way. This is also nicely agrees with the experiment. So finally, I just want to mention, just recently together with our master course student, we extend our analysis to the negative parity state, the resonance, the decay of this state. Experimentally, this is known by making wave functions of this state in the holographic model by using the wave functions of the z coordinate extra dimensions. That is for the negative parity. We have found this kind of closed expression. This also agrees with pretty well with experimental data. Okay, so here is a summary. So let me first summarize the holographic model. Seems to be interesting, nicely agrees with experimental data. But what I want to emphasize here is that the holographic model is actually dynamical, actually collective model. And this collectivity shows up somewhat different features from the non-relativistic quark model. But of course, quark model itself works well. And that is the first issue for TQQ. Thank you very much.
Thank you for the very interesting talk. I just had a quick question. So for these doubly heavy tetraquarks, you said that the tightly bound one is when the two heavy quarks form a diquark, right?
Yes. Yeah.
What about the light quarks? Can you think of those also as forming some kind of loosely bound diquark, or? And then,
your question is that when we change the kinds of quarks of heavy quark to light quark?
No, just the picture you showed. You had the two Bs very close by, right?
Like this.
Yeah, this picture.
Yeah, okay.
Can you think of the two light ones as also kind of loose diquark?
Yeah. This is whether we should say loose or tight depends on the matter of taste. Probably to some extent matter of taste. But roughly speaking, I would say that this one, two heavy quarks, is really tight. I would say the average distance is, let me see, 0.3 Fermi or something. But the distance between this and there, I think this is drawn by a black curve in here. And the distance between two light quarks is red. They are very similar, like 0.6 or 7 Fermi. So therefore, I draw this kind of triangle diagram. They are rather closely compact, but the other two distances are more or less similar.
Does your model predict for doubly heavy variance, say BB light variant? Does it give results comparable to other models? Or? Yes.
Right. Yeah.
Okay, so yeah, we have very short time. Marek.
Yeah, just a comment, Igor. following up on your question, we sort of know that the two light quarks have to form an isospin spin zero diquark. And when you talk about tightly or loosely bound, the point is that energetically, it's quite tightly bound. It's 200 MeV, more bound than a diquark with spin 1. But the two light quarks are not particularly close to one another. The average distance is something like Atsushi had shown, but it's crucial that this is a spin zero isospin zero diquark, because it's a very clear prediction of this model that the tetraquark is an isoscalar. Otherwise, you get an isotriplet. So it's very important.
Great.
Can I add just a short, I would say, remark? Namely, that this diquark feature in our four-body calculations is actually taken care of by this spin-spin interaction. And if we calculate the spin-spin interaction exclusively, as Marek says, that this has some attraction like 200 MeV for the so-called good diquark pair of Q bar Q bar. But actually, after computing explicitly the four-body state, we have found, although the attraction is large, but actually the phase space structure looks like this. This seems to be the fact.
Okay, last question, Arkady.
No, it's just continuation of the same in certain way, because when you consider these two heavy B quark, I wonder, this it's whether the Coulomb interaction is attractive or repulsive, right? It depends on this color state, and I do not. But so when you're saying it's tight, I'm not sure whether it's attraction or repulsion.
Okay, it can be either very strong attractive or relatively weak repulsive. But after solving the system, this is the we are trying to find the minimum configurations of this four-body state. So therefore, the strongly attractive channel is dominated. So eventually, the attractive channel works effectively, almost exclusively. That gives this sort of configuration.
Okay, thank you.
Okay, thank you very much.